Okay, thank you. Thanks to everyone for being here. So I'm going to be presenting a short-term planning framework that's going to be incorporating a few different things that we've been developing for years here at Findlay. I'll start with some introduction and then get into the method of what we're proposing here. I'll show you an application using a gold mine complex, and then we'll finish up with some conclusions and future. So of course we have an industrial mining complex where we have material being extracted from multiple mines, being transported and processed through different processing streams, and ultimately transformed into valuable products that we sell to customers. What I want to highlight here is that we have numerous sources of uncertainty. So you've heard of a few different types of uncertainty already today. And what we're going to look at in this presentation is specifically two of them. So of course, we have uncertainty in the material properties that we represent using simulated ore body models. And we have a second type of uncertainty in the processing performance. So in those transformations that happen to the material in our processing streams, we know there's uncertainty in there, and so we want to include it into our mine planning framework. We're also working with this concept that we've been working with for a few years, which is the closed loop mining framework. And the way this works is that we have a mining complex, and every day that we operate, we're collecting a huge amount of data, and it can be from a wide variety of sources, sensors or measurements that we're collecting. It could be related to the properties of our material, the performance of our equipment, the performance of the processing plants, any types of data we want to be able to collect and use it. What do we use it for? Well, first of all, we want to update our models of uncertainty. So the things that we don't know for certain beforehand, that we collect the data for, we want to use that data to update our understanding of what's in the ground, what's happening in our processing facilities, and so on. The next thing that we can use this for is updating our decisions that go into our production schedules and our mine plans. So changing our extraction sequence or our destination policy in lieu of the new information that we collected is where the value comes in, so we can make better decisions going forward to take advantage of the data that we're collecting today. And finally, close the loop by executing the schedule using the adaptive decisions. And so we can continue doing this process over and over. The part that we're going to focus on in this presentation is about adaptive decisions. So particularly in short-term planning of the mining complex. Okay, so what kind of decisions are we including in this short-term production planning framework? The first one that we're going to look at here is the shovel decisions. So where are we putting our shovels? What blocks are they going to be mining? And basically that's going to form our extraction sequence. We also have destinations. So where are we sending this material, whether to a waste dump or a stockpile or to be processed. We also have processing stream decisions. So if we have multiple processing streams, we need to figure out how to route our material through our mining complex. And another type of decision variable that we want to include here is operating modes. So we could have different processing facilities, and these facilities might have different operating modes, and want to be optimizing the choice of those modes with these other decision variables. So for example, if we have a screen separation facility, that we can control the aperture of the screen setting. That's a decision that we want to include in this type of framework. Another example could be if we have a grinding mill where we have coarse with fine grinding modes that we want to look at as well. Every decision depends on the material properties. So ultimately, what's in the ground is what's going to drive the performance of all of these aspects of the mining complex. So everything comes back to what do we have in our material? But there's another aspect that's very critical to the performance of the mining complex, and that is material transformations that we have in our processing facilities. So in reality, we have material being mined, blended, crushed, stockpiled, blended again, and then sent to some sort of processing stream. And then what we get at the end of this is valuable products, metals or other products that we can sell to customers. But when we're doing planning, what we actually have is some sort of model that takes in the material properties that are represented by numbers and does some sort of modeling. It could be many different types of models, but the essence is that it gives us a predicted performance for what we're going to have in one of these processing facilities. So it could be metal recovery or grinding throughputs. And this model could be, a regression, it could be a neural network, it could be any sort of, function that takes the material properties and gives us a prediction of what we'll get from processing those materials. But as I mentioned, the closed loop framework, we're collecting a huge amount of data from our mine complex, and we can be collecting data from the material. So maybe when it's still in the ground, or maybe after it's been crushed. Here we can see example of a scanner on a conveyor belts that can give us some information about the material. And we can also collect measurements from the outputs of the processing facilities. So if we have measurements on the quality of the resulting products or the performance of what's happening during that processing, and we can collect these measurements. And so what if we actually try to use more of a data-driven approach to representing this transformation instead of a model which can be subjective or limited in some way, even if it's very advanced. And so the closed loop mining framework motivates a data-driven approach for modeling material transformations. Because we have all of this data, we want to use it to make the best prediction that we can and ultimately drive value in our plant. So the type of method that we're going to use in this work to represent those material transformations is actually to look at a simulation framework using high order simulation, where we can predict the performance of our mineral processing with some nice advantages. So what it can give us is a prediction of performance that has variability and uncertainty included in the resulting prediction. So any sort of deterministic methods like a regression would not be able to give you that, even though we know that these results in reality can be quite variable. Some other benefits of this type of framework with the higher order simulation is that we don't assume any distribution on the underlying process. We can consider multiple attributes that we have in our material to predict a given performance metric. We're able to consider operating modes. So if we have a processing facility and we have historical data where the operating mode is labeled corresponding to a certain performance outcome, then we can use that data to forecast, with those operating modes being included. And one more nice thing that's, becoming more and more critical in our research is that we're looking at geometallurgical attributes which can be non-additive. So what's nice about the simulation framework is that we can use proportional data that represents the attributes of the material instead of just being limited to having to take an average value for whatever the attribute is. So we can use proportions to pass in more information about our geometallurgical attributes and get a simulated performance distribution. In terms of actually making the planning decisions, we're using kind of a combination of two different frameworks to make these decisions. One of them is reinforcement learning. And what's nice about reinforcement learning is that it can train offline and then update decisions when new information is acquired. So it fits very well with the closed loop mining framework. We can have multiple agents that handle the different decisions. So like I mentioned earlier, we have several different types of decisions that go into our plans. But as I mentioned, some things can still be optimized using other methods like typical optimization frameworks or meta-heuristics as well. So we can have both these approaches and ideally kind of take the best of both techniques to try and build our short-term plan. So getting more into the method, I'll start by outlining the stochastic integer programming formulation. So we have four main decision variables. We have when we're going to mine a given block, what block or what destination we're going to send that block to. We have a decision that is responsible for sending material throughout our different processing streams, so our downstream flow. And then we have a fourth decision variable that we're including here, which is which operating mode we're going to include or we're going to use at each facility in each of our time periods. So we have this objective function with four components. We have the discounted cash flow, which we're trying to maximize over our planning horizon. And then we have some costs. So we have a cost of using certain operating modes. If different operating modes have different costs associated with them, we can include that. And we have two sources of penalties. The first one, which is the short-term penalties, is measuring deviations from targets that we have in each short-term period. So if we're building a 12-month plan, for example, we have a mill capacity each month, that we need to hit. So we're going to penalize any deviations from those targets. And then the second source of penalties is what I'm calling the end-of-year penalties. And that's about complying with targets that we get from the long-term plan. So, for example, if the long-term plan says we want a certain amount of material to be in a stockpile by the end of the year, then we want the short-term plan to comply with that. So we're going to penalize any deviations there. And then something else to highlight here is this RH, which represents the set of scenarios for the simulated processing performance. So you can see with the S and then the R, we have these two different sources of uncertainty coming from one coming from the ore body simulations and then one coming from the simulated processing performance. So these are going to be combined and both represented. Looking into more detail of our processing performance simulator, the way this is going to work, as implemented in the method, is that each time we're trying to evaluate our short-term schedule during the optimization, we're going to have a set of decisions coming from the schedule. So, which blocks are we mining in this period based on our shovel decisions. That's going to tell us, what is our set of material properties for this given period, and then that's going to be passed into the simulator, and then we'll get an output of the simulated processing performance for each of our different performance metrics that we're tracking. As I mentioned before, the simulator is going to infer the statistics from the historical data. So those high-order statistics that have been inferred of before, I won't go into too much detail here, but that's going to be represented from our past data. And something else to note is that we're going to simulate the processing performance on each ore body scenario individually. So for a given ore body simulation, out of if we have 10 of them for the first one, we're going to have let's say another 10 simulations of the processing performance, and so these are going to sort of multiply. But those are all going to be accounted for in the objective function when we're trying to add up our results. Okay, so as I mentioned earlier, we have multiple decision types, and so we're going to use multiple reinforcement learning and optimization agents to make each of these decisions. So the first one, after we start, from a blank short-term schedule, our first agent is going to choose the shovel actions. So where the shovels will be going and what blocks they're going to be mining. Then this information, the chosen actions for the shovels are going to be passed to destination agents, which is going to choose for all the blocks that are being mined, what destinations to send each of those blocks to. So now we know, roughly what material we're mining and where it's going to be going. And so then the operating mode agent can take this and choose what will be the best operating modes for each of our processing facilities. And then finally, with most of the schedule built, we can optimize the downstream flow decisions. So things like material going in and out of stockpiles, or if we have multiple connected processing streams, material going through those. But instead of using the reinforcement learning agent, for these we can actually use stochastic manager programming with a more traditional optimization method. So we can make the decisions, and then actually now that we have a complete schedule, we're going to simulate that processing performance and use that to evaluate the results of the schedule and put that into the objective function. And in this last step, we can iteratively optimize those downstream flow decisions to complete the schedule using any heuristics or any other stochastic optimization approach. Okay, and so this gives us our final solution. So we have all of our decisions being made. And in the case that we're still training the reinforcement learning agents, that final solution value node is given to those first three decision makers, and they can use that outcome to train from that experience. And without going into too much detail, the reinforcement learning algorithm that was used for this project is deep Q learning. Okay, so to look more closely at the actual agents, we'll start with the shovel agents. So the actions that I can choose from are going to be the closest blocks that are exposed and available for mining. So if you can see here, the different gray tones represent the benches that we have at any given mine, and these blocks with the blue X's represent the blocks that are exposed and available for mining to be considered next for this shovel. And so the information that it's going to use to make its choice is, of course, the simulated block properties for each of these blocks. But we're also going to give it the simulated properties of the blocks that are around those blocks. So underneath it or behind it. And that way it's going to actually be able to plan ahead a little bit using that information. And as well, it's going to be told the time required to move to each of those blocks and the amount of time remaining in the current period. So it's going to be able to balance, what's the best block versus, is there actually time to move the shovel there? So it's going to inherently minimize the shovel movement time while optimizing the schedule. As well, we can give it any relevant production targets that might be important. Looking at the destination agents, we have the different destinations that are available in the mining complex as the possible actions. In terms of the state, the information that will show to the agent would be the simulated block properties for the given block that's being looked at. We're also going to give the simulated properties of the blocks that have already been scheduled to destinations, as well as the properties of the blocks that are supposed to be mined in this period, but have not been given a destination yet. And so the agent will be able to sort of understand where does this block stand relative to the other material that we mine and pick an appropriate destination. The operating mode agents will be choosing from the different operating modes that are available for each processing facility. Each facility will actually have its own agents because each one will need to learn its own things related to that specific processing facility. So it's going to choose the modes that are available based on the simulated properties of the incoming material. So the material that's been scheduled for mining and then going to a certain destination. It's also going to be given the simulated properties of the stockpile material. So at this point, because the downstream decisions are made after, we actually don't know if if any material would be coming from the stockpile into these facilities. But the idea is that through the reinforcement learning, it's going to learn to identify, based on the material it knows it's coming and the material it knows is sitting in the stockpile, it can still make, an optimal choice through that experiential training. Okay, so looking at putting this all together into an application, we have gold mine complex. We have 2 mines with 3 simulated attributes. We have gold, sulfur, and material hardness. In the mining complex, we have a waste dump, stockpile, and then 1 processing stream where we have a screen separation facility, a grinding mill, and then finally a flotation plant, which is going to give us our final gold products. We're building a 12-month schedule. And so to look at the processing performances that are going to be simulated, we have mass pass through screen. So this is at our screen separation facility. And the data that's going to use to condition the simulation are the material properties that are entering the screen and the screen size. So that's the operating mode screen size that will have been chosen. And I'll simulate the mass that's going through the screen. The next one that we're going to simulate is the amount of gold passing the screen. So this will be conditioned on material properties, the screen size chosen, but now it'll actually also include what we just simulated, the mass passing, as conditioning data for simulating gold passing. So now it's actually a sequential simulation where each sequential process performance attribute that we're simulating can take into account the previous one that we just simulated. And the last one is going to be the gold recovered from flotation. So now we can, it's building, as you can see this information, so it'll take into account material properties, the mass and the gold past the screen. And now it'll also include the grinding mode that's been selected at the grinding mill. So those will all go into account and use it to simulate the final gold recovered from the flotation plant. Okay, so we're going to look at 2 different schedules. So we have on the left, we have the stochastic processing performance schedule, which is what I've been explaining. That's the method that we're proposing here. The one on the right is mostly the same, except instead of simulating the processing performance, it's just using a simple regression to model those material transformations. Okay, and so there's not much to see, just from looking at these images, except that they are different. So, they have chosen different, extraction sequences for the 12 months, and we'll look in more detail about, where those differences will have effects. Here we can see the material that's being scheduled to go to 2 different destinations in our 12 months. So we have material going to the waste dump, the stockpile, and then straight to the screen. For each of our 2 schedules. Again, we can see that they are different. So then how will this impact our results? Next, we'll look at the screen size. So, we've chosen from 3 different screen sizes, actually. We had 30, 50, and 100 millimeters. So interestingly, neither schedule ever chose the 100 millimeters. So I guess it just wasn't a very good option in this case. But again, we can see that the 2 schedules have chosen different screen sizes. And here we can see the mass passing the screen. So now we can look at how are these choices impacting results. In orange, we have the base case with the regression model. And in blue, we have stochastic schedule with the risk profile based on our sources of uncertainty. So we can see that both schedules are fairly consistent and actually not a lot of variance in these risk profiles. And that's actually just because the tonnage was not simulated in the material. Just the grades of the attributes are simulated. And then the historical data that is based on just did not have a very high variance. So that's why you're seeing these relatively narrow risk profiles. However, we do see, in the base case, there is significant amount of variability that we get in later months. So something to be aware of. Here we can see the gold pass on the screen. So this is fluctuating quite a bit more, and that's because of those different screen aperture size choices that have been made. So those really impact the amount of gold that's going to be passing. And again, we can see they're fairly similar, fluctuating quite a bit. We can't really see again which one is better. So let's keep looking. And now we can see the amount of gold recovered. So on the right, we can see the choices made for the operating modes of the grinding mill, and they actually made mostly similar choices. Making fine grinding in most months, but there are some differences. And we can see in the gold recovered over the 12 months that actually the stochastic schedule is consistently producing more gold. So, based on the risk profiles, we can see that, having the information of the full range of uncertainty in those processing performances, the stochastic schedule that was able to see those while optimizing, has created a schedule that yields consistently more gold. And we see pretty similar trends when we look at cash flow over the 12 months. So the stochastic case that that can see this full range of uncertainty was able to take advantage and produce a schedule that yields more gold and makes more money over the 12 months. So that's a nice result. Some conclusions. So we presented a short-term planning framework that includes operating mode decisions integrated in planning. We have a high-order processing simulation that gives us data-driven stochastic forecasts of our processing performance that we can use during the decision-making to make better decisions. We also had a multi-agent reinforcement learning and optimization framework that uses the best of both techniques to enable this adaptive short-term planning system. And just as a reminder, the processing simulator, what's nice about it is that it can be updated as we collect new data. So if things change in the mining complex or the production changes, that new data can be really useful in updating our understanding of what's going on in those processing facilities. To look at some future work, one thing that we talked about, but want to do more in the future is link short-term planning and long-term planning. So try to include this long-term planning framework. Of course, we always want to develop case studies with a wide range of different contexts or situations. So we can look at new operating modes or other performance metrics that we can simulate in a case study. And then something else you've heard about today is exploring further integration of these new and innovative methods for optimizing production schedules. So that's all I have, and thanks for listening.